yesterday we discussed about a very important equation that is called as Arrhenius equation. So basically in the yesterday's class we discussed about the effect of temperature on the rate constant. Now we could clearly see from the Arrhenius equation that the rate of a reaction increases exponentially with the increase in temperature. Okay. So we derived the equation that was K is equals to A into e raised to minus EA by RT. EA was the activation energy, R was the gas constant, T was the temperature, K is the rate constant, and A is called as pre-exponential factor. Okay, or it is also called as a Arrhenius constant. So let us start the concept with, let us modify the concept of that was given by Arrhenius, and we will develop a new concept known as collision theory. Before going into the collision theory, let us do some solving. Okay, so let us look at this reaction. Okay, so this is basically a reaction. This we had attempted in the previous lecture, but I think the question was wrong due to printing mistake. So I am basically revisiting that question. So in this question, it is said that there is a reaction between, now A is getting transformed into B in an equilibrium reaction. The rate constant of the forward reaction is K1, rate constant of the backward reaction is K2. Okay, and in the second step, basically B is reacting with C and forming D. The rate constant of this is K3. Now if we add both the reactions, we will get the overall reaction. So B gets cancelled out and we will get the reaction as A plus C changing into D. So in the question for this overall reaction, we have been said that we have to find the rate of the equation of this given chemical equation. So in this, let us assume the slowest step to be the second step, and this is the fast equilibrium. Okay. So basically we know that whenever a complex reaction has been given to us, we have to see the rate determining step, okay, or that elementary step which is slowest. So basically out of these two reactions, these two elementary reaction, second step is the slowest step. So basically I can write this as rate is equals to K into concentration of B raised to power 1 into concentration of C raised to power 1. Okay, so this is the rate equation. Okay, so I hope this is clear to everyone because this is a elementary reaction. So order with respect to B is 1, order with respect to C is 1. Now we can clearly see that the main reaction was A and C giving D, but in the rate equation you can see that there is a new component B. Now as you can see in the reaction, B was formed as an intermediate in the reaction and it was consumed immediately. So we can say that B is an intermediate in this case. Okay. Now we know that we don't have to express the rate in terms of the intermediate because intermediates are consumed in the reaction. So basically we have to apply steady state approximation on B and get the concentration of B in terms of other reactants. So let us try to apply the steady state approximation on B. Now if you look at B, okay, so I will say that B is an intermediate, so change in concentration of B with respect to time is 0. I am applying steady state approximation to B. Okay. So as we can clearly see that in the first reaction B is formed. Okay. So in this, when B is getting formed, A will be the reactant. Okay. So dB by dt I can write as K1 into concentration of A. Okay, because through this reaction B is getting formed. Okay, so I will write minus dA by dt equals to dB by dt equals to K1 into A. We are considering only the forward reaction. Now if you look at the backward reaction, through backward reaction B is getting consumed. Okay, so when it is getting consumed, B itself is acting as the reactant. So because it is consumed, so I will write this as minus rate constant is K2 and the reactant over here is B. Okay. Now let us look at the third step. In the third step again, or in the second step rather, it is again B is again getting consumed and reactant is B and C in this case. So rate would be K3 into concentration of B into concentration of C. So basically this is minus K3 into concentration of B into concentration of C. This has to be equal to 0. Okay, so I can write this as K1A equals to, just take B common, so I will write this as K2 plus K3 into concentration of C. Okay, so I can write the concentration of B as K1 into A divided by K2 plus K3 into concentration of C. Okay, so I hope this is clear to everyone. Now when we put back the concentration of B in the equation, so rate basically was K3, so this will become K1 into K3 upon K2 plus K3 into concentration of C, okay, into concentration of A into concentration of B. Sorry, what I am writing. Let me erase this first. This scarcity of space over here. So when I put the value of B from there, so I can write rate as K3. B we know is K1 into concentration of A divided by K2 plus K3 into concentration of C. Okay, so this is again a C over here. So this is the final rate equation. Okay, so you can clearly see that this is the rate equation. Okay, so this is how you apply steady state approximation. Okay, so I hope you have understood the concept of steady state approximation. Basically you have to look for the intermediate and the change in concentration with respect to time has to be 0. So basically dB by dt you have to find out, because in this reaction it is getting formed, so rate would be K1 into concentration of A raised to power 1. In the backward reaction it is getting consumed, so this will be minus K2 into concentration of B. In this reaction it is again getting consumed, so this will be minus K3 into concentration of B raised to power stoichiometry, that is 1, into concentration of C raised to power stoichiometry, that is 1. So we are equating this with 0. Okay, so this is the approach of steady state approximation. Okay, so I hope this is clear to everyone. Now let us look at the other question. How can the activation energy for a reaction be determined graphically? So we know that K is equals to A into E raised to minus EA by RT represents the Arrhenius equation. So when we are taking log, so we will write this as ln K equals to ln A into E raised to minus EA by RT. So we know that ln x into y is ln x plus ln y. So this is ln A minus EA upon RT. Okay. So if you plot ln K versus 1 by T. Okay, so if you plot ln K on the y axis and take 1 by T on the x axis, so this is y equals to mx plus c, so this is basically c. So this is basically having an intercept of ln A. So this would basically be ln A, and this is having a negative slope, so this would go like this. Okay, the slope of this line would be minus EA by R. And if you are plotting log base 10, then the slope would be minus EA upon 2.303 R. Okay, so again a very straightforward question. I hope this is clear to everyone. Okay, so let us look at this reaction. Try to solve this reaction. Okay, try to solve this question. I will give a solution. Try to solve this word first. So basically in this, a first order reaction has been given to us, and the temperature rate constant dependence has been given to us as log K equals to minus 2000 upon T plus 6. Okay, the pre-exponential factor we have to calculate and the activation energy. Okay, so basically if you look at this equation, this is equation of the format, okay, of the Arrhenius equation. So if you take log, so we'll get, we have already done this, this is log K, this is log A minus EA upon 2.303 RT. So basically the given equation that has been given to us is of this form. Okay, so just we'll compare this. So we know that log of A will be equal to log base 10, A will be equal to 6. So the value of Arrhenius constant A would be 10 raised to power 6. Okay, Now if you look at this term, so basically you will compare this term, so I can clearly see that minus EA upon 2.303 R would be equal to minus 2000. Okay, so this minus minus gets cancelled out, so I can write EA as 2000 into 2.303 into R I can take as 8.314, so I will get the answer in joule per mole. Okay, so I hope you are able to understand this. Okay, so just I can see very much through this equation that this equation was of the format something like this. So basically I have to do the comparison, so I can do the comparison. Log A was equal to 6 and this quantity is equal to this, so we can calculate A as well as EA. Okay, so I hope you have understood this question. Okay, so you can just note it down. Okay, so let us go to the next question. The question says that the Arrhenius equation for the rate constant of decomposition of methyl nitride and ethyl nitride are as given. Okay, the reaction has not been given to us. Only thing which has been said to us is that methyl nitride is decomposing and its rate equation is something like this. Okay, the rate constant expression is something like this. Whereas for that of ethyl nitrate, the rate constant expression is something like this. Now this says that find the temperature at which the rate constants are equal. So basically we have to do K1 equals to K2. Okay, so when you write this, this is 10 raised to power 13 e raised to power minus 152300 upon RT equals to 10 raised to power 14 e raised to power minus 157700 upon RT. Okay, so this will basically cancel this, so 10 would be left over here. So let us take the log. So when you take the log, this will become minus 152300 RT. Okay, so this would be ln 10 minus 157700 RT. Okay, so you can take this over here, so this becomes 157700 minus 152300 divided by RT equals to ln 10. I can write this as 2.303. Okay, so temperature in this case would be, you have to just subtract this, so this is basically 0045 upon 2.303. Okay, because everything is given in joules, so we have to take R as 8.314. So when you do this, we get the temperature in Kelvin. So again a very straightforward standard equation questions, but these questions help you in doing a lot of calculation, and that makes your calculation skill at a very good level, and you are able to number crunch it easily. So these types of questions are important, even though it will look like these are basically formula based questions, but we have to assure that we are doing all the required calculation so that our skills are improving and we are able to get the right answer. Okay, because in integer type questions there are mostly questions that we have to express up to 2 decimal places. So for that we need to have very good calculation skills. Okay, so I hope this question is clear to everyone. You can take a snapshot. If you have written, you can write it down as well. Okay, so now let us enter to the next important theory for explanation of temperature dependence, or for explaining the Arrhenius equation in a much better manner, that is collision theory. Okay, so basically this we have already discussed in the previous lecture, but we have not discussed in the form of a particular theory. We were just saying that reactions are always a result of molecular collisions. So basically the postulates of collision theory is, firstly we'll assume the atoms or the molecules to be hard spheres. Okay, so while they are colliding, okay, there will not be any deformation of those shapes. Okay, so basically we will assume the molecules and atom to be hard spheres. So the first postulates of collision theory was, the products are formed only when the reactant molecules come close and they collide with each other. Okay, so this I have already told you. Whenever there are reactants are in random motion due to their inherent kinetic energy. Okay, so they are moving here and there. While movement, they can collide with each other. Okay, so when the reactant molecules come close to each other and they collide to each other, they can transform into product. but all collisions do not result into a chemical reaction. Okay, only certain specific collisions would be allowed that would result into the formation of product. So basically only those collisions are effective in producing the product which satisfy a minimum criteria, that is a criteria of energy of activation and specific orientation of molecules. Okay, so basically what I am saying is, if you look in general in any reaction, the number of collisions would be something around 10 raised to power 23 to 10 raised to power 25. So that's a very huge number of collisions that is happening inside a container between the reactant molecule. But if all the collisions were effective, if all the collisions were leading to the product formation, then the reaction should have completed very quickly. But that is not the case. Most of the reaction takes a time, some reaction takes a lot of time in like producing the product. So basically we will say that when the molecules are colliding with each other, all collisions would not result into the formation of product. Only those collisions which brings about the transformation of reactant into products or which results into the product formation are called as effective collision. So there are two different concepts. Collision is the total number of collision that is going on, and effective collisions are those collisions which brings about the molecular rearrangement in reactants and they convert them into product. Okay, so basically you have to write these points, just write it down. Okay, so we are talking about now effective collisions. Total number of collisions are not of any use for us. We need to understand what are effective collisions. Okay, so effective collisions are those collisions which brings about the transformation of reactant into products, and not all collisions will be effective. Okay, so lot of conceptual theoretical questions are based on this topic which definitely comes in JEE Advanced. Okay, if you look in the paper in JEE Advanced 2017, there was a direct question on collision theory. So theoretical knowledge is very important. We tend to neglect the theoretical aspect. We mostly try to focus on problem solving, but believe me, a good level of problem solving will help you in cracking the numerical questions. But if the questions are theoretical, you need to have the theoretical aspect as well and have a very good notes with you. Okay, so let us try to understand the important barriers to a reaction. So basically we are saying that when reactants are mixed, due to their inherent kinetic energy, they will have molecular speeds, they will have certain kinetic energy, they will keep on moving here and there, and in the process, in this random process, they would collide with each other, and during collision they would impart some energy to each other. Okay, now if that energy is equal to a minimum energy, then we say that the reactant transforms into the product. But again, not all molecules on collision will have that particular energy. So only few molecules will be able to transform into the product. So only those collisions which brings about this transformation of reactant into products is called as effective collision. So the first important barrier is the energy factor. Okay, so we know that there will be many collisions, but all collisions would not be energetic enough to bring about the transformation of reactant into product. So basically we have to look for those collisions which are energetically favorable to form the products. Okay, so we'll say that for a collision to be effective, the colliding molecule must have energy more than a particular value. This minimum energy which the colliding molecule must have in order that the collision between them may be effective is called as threshold energy. Okay, so we have introduced a term known as threshold energy. Okay, so I have already demonstrated this in the previous lecture in the Arrhenius equation. Suppose we are plotting energy diagram profile of a reaction, right? So we are plotting energy with reaction progress. Okay, so we'll say that when the reactants are colliding, okay, during the collision they will give energy to each other. If the energy of the ensemble is greater than a minimum value, then the reactant would transform into a product. Now the minimum energy required is called as threshold energy. So suppose I was plotting a graph, so this was basically a reactant, suppose this was the product, so this was the plot of, okay, this was the plot. So basically we are saying that this energy, okay, this energy is our threshold energy. So this is the minimum energy, okay, that is required for the reactant to change into product. Okay, so this minimum energy is called as threshold energy. So if you look at this, this was your energy of reactant, okay, from the, this was your activated complex, or we have already defined this as the transition state. So activated complex, the difference in the energy between the reactants and the activated complex is your activation energy. So this was basically activation energy of the forward reaction, okay, and this is basically the energy of the reactant. So threshold energy is basically, okay, so threshold energy will be the average energy of the reactants, okay, so the energy of reactants plus the activation energy. Okay, so I hope this is clear to you. So the molecule, because the reactant have certain energy, because reactant itself will have a certain energy because of the kinetic energy that it possesses. So basically it would require this amount of energy to transform into product. So basically if we give this reactant this much amount of energy, that is equal to activation energy, this reactant will come to this state. We know that in an activated complex or a transition state, this has a very high energy and is very unstable and is possessing a very large vibrational energy. So due to which this is unstable and this is going to roll down into the product which is at the lower energy. So that is how this reaction is proceeding. Okay. So the difference in the energy between the reactant and the activated complex is called as the activation energy. Okay. So if you see, threshold energy is basically the entire, like from the zero origin to the activated complex. Okay. So this energy is called as the threshold energy. So if we define activation energy would be, okay, so activation energy is generally written by EA. So activation energy would be threshold energy minus energy of reactants. Okay. I hope you are parallelly making the notes, okay, and not just listening to the videos. You are just making the notes also. So if I look at this reaction as this also, I can say that if I want to change the product into reactant, so if I want to carry the backward reaction, so we have to cross this barrier, the product has to cross this barrier, so it will form the product. So this will basically be the activation energy of backward reaction, and this is activation energy of forward reaction, and we know that this is the energy of product. So the difference between the energy of product and the energy of reactant is your overall delta H reaction. Okay. So I can also say that delta H reaction is energy of product, P is your product, minus total enthalpy of reactant or energy of reactant. I am showing it by E, but it is actually enthalpy. Okay. Or also we can say that activation energy of forward reaction plus mod of delta H, okay, should be equal to activation energy of backward energy. So from this we can form the magnitude of enthalpy of the reaction. But if we know that activation energy of backward reaction is more, that means this delta H will always be negative. Okay. So just write it down. So we are saying that whenever molecules are colliding, they will transfer energy to each other. If the energy of that ensemble of that particular time becomes equal or greater than a minimum energy required, then the product will transform, then the reactant would transform into the product. So basically the minimum energy that is required for the reactant to transform into product is called as threshold energy, and activation energy would be the energy required by the reactant, because energy, there would be some energy that is possessed by the reactant also. So basically this is entire threshold energy and this is the energy of reactant. So if you subtract, you will get the activation energy. Okay. So I hope this is clear to everyone. Okay. I hope everyone has written this also. Okay, so let us draw the graph. Now if you look at this graph, this is basically a graph of a exothermic reaction. Okay, because we can see that delta H over here would be negative. Okay, so if we want to draw the graph for a endothermic reaction, okay, so if we want to draw the graph for a endothermic reaction, for endothermic reaction we will know that delta H is positive, so energy of product should be greater than energy of the reactant. Okay, so this is the graph. So suppose this is the reactant and this is the product. We can clearly make out that the energy of product is greater than energy of reactant, so the delta H of this reaction would be positive. Okay, so this is the energy of reactant, this is the energy of product. So if you subtract them, so this is our delta H of reaction. Okay, so if we want to convert this reactant into product, we would need to give this molecule, okay, energy that is equal to the difference between the peak and the reactant. If we provide this much energy, that is activation energy, to this reactant, so this reactant will go over here and this is going to form a transition state or the activated complex, which is highly unstable, and it will transform into the product. So basically this would be the activation energy of forward reaction. Okay, and if we want to convert product into reactant, so this would be basically the activation energy required. So if we give this much amount of energy, activation energy EAB, to this P, then it will transform into R. So basically for any reaction to happen, we have to make the reactant cross the barrier. So basically the energy required to cross the barrier by the reactant is also called as the activation energy. Whereas if you look at the threshold energy will be the, okay, this, the energy from the origin. So this is our threshold energy. So energy, minimum energy required for a reaction to proceed or reactant to convert into product is called as threshold energy, and the energy that should be given to the reactant so that it transforms into the product is called as activation energy. So the difference between the two. Okay, so I hope this is clear to everyone. Now when you look at the expression K is equals to A into e raised to minus EA by RT. Okay, someone asked me, sir, what if EA is 0? Okay, so if EA is 0, that means activation energy is 0. That means there would be no peak. Okay, so basically this will come to a level. Okay, but if activation energy is 0, we can clearly make out that K is equals to A upon e raised power EA by RT. Okay, so if EA is 0, then e raised power 0 would become 1. So basically K would be equal to A. Okay, in the previous lecture I have told that A basically signifies the total number of collisions with proper, or rather it represents collision frequency with along with the steric factor. So it represents only the effective collisions. Okay, so if K is equal to A, it means all the collisions that are happening becomes equal to the rate constant, which is not possible because all collisions are not effective. So EA cannot be 0. Okay, so we say that EA cannot be 0. Similarly, suppose if EA is negative. Okay, so if EA is negative, we can write K as A into, if we take the value, so this becomes EA by RT if EA is negative. Now we can apply the binomial expansion. So this will become basically, suppose this quantity is taken as x, so it will become 1 plus x square and so forth. So basically I can make out that K is much greater than A, okay, which is again not possible. A was representing the collisions, so K cannot be greater than, the rate cannot be equal greater than the all the collisions that are happening, okay. Neither K can be equal to A, because if it is equal, it means that all the collisions are effective, which is not the case, okay. And we have already discussed that e raised to power minus EA by RT is called as Boltzmann factor, okay. This is called as a Boltzmann factor, and it represents fraction of molecules, possessing, okay, it represents fraction of molecules possessing energy greater than equal to activation energy, okay. So basically in the Arrhenius equation, this term is basically the Boltzmann term that indicates the fraction of molecules that has energy greater than equal to activation energy, okay. So I hope this is clear to everyone. So basically we are saying that whenever, according to collision theory, a reaction is happening due to result of collision between the reactant molecules, when they are colliding with each other, so they are imparting energy to each other. Now if this energy is greater than a minimum value, that is called as threshold energy, then the reaction would proceed, okay. So that means all the collisions are not effective in bringing about the reaction. Only those collisions which bring about the reaction, that is reactant is getting transformed into the products, those collisions will be called as effective collision, okay. So we have drawn the graph for endothermic reaction, exothermic reaction, understood the concept of threshold energy, activation energy, and delta H of reaction, okay. Also we have come to understand that this quantity represents the fraction of molecules possessing energy greater than activation energy, okay. So I hope this is clear to everyone. So the first criteria that should be met by the colliding molecules to transform into the product is the energy factor. Energy of the colliding molecules or during the collision must be equal or greater than a minimum energy. Then only the reactant can transform into the product, okay. Now second very important point is orientation factor, okay. Now let us understand what is orientation factor. In some cases, it is found that even if a larger number of colliding molecules have energy more than threshold value, still the reaction is slow, okay. This is because of improper orientation of the colliding molecules at the time of collision, okay. So let us understand it through some example. Like this is a very easy and a pictorial type of concept which can get into the head very easily. So basically it is saying that only energy criteria is not sufficient to say that the collisions would be effective. Like the colliding molecule like may be having energy more than the threshold energy, but still it might not result into the product formation. So let us understand through the example, okay. Now let us consider a hypothetical reaction, something like this, where two molecules of AB are reacting to each other and they are suppose forming A2 and B2, okay. I hope this is clear to everyone, okay. So suppose there is a reaction in which 2AB is decomposing into A2 and B2, okay. So this is the primary reaction which is happening. So what exactly is happening, as we can see through the collision theory. Now we are having AB molecule, okay. Suppose we are representing A as the spherical hard sphere, B as a hard sphere, A has a greater size than B. Similarly another AB molecule. Now it can happen that these AB molecules are colliding with each other, right. So when they are colliding with each other, we can clearly see that A is making contact with A and B will make contact with B. So basically when it makes collision, they can transfer energy to each other, and if this splits away, so basically A will come out and BB will come out. So A2 and B2 will be formed. Now consider another scenario, because in a reaction mixture or in the container, all the collisions will be random. Okay, so there is no one specific type of collision that is happening, because reactant can collide in any manner. Okay, so that cannot be generalized that it is only reacting in a particular orientation. There will be different types of collisions that are happening. So let us consider another type of collision that could happen over here is, suppose this is A, this is B. Okay, they are bonded together, and suppose this is A and B. So this AB molecule is now approaching this AB molecule and they are about to collide. Now when they collide, you can clearly see that this is A is combining with A, or A is colliding with B, and this A is colliding with this B. So when they split up, we will form AB and AB. So basically we are getting back the original reactant molecule. So these collisions are not effective. These collisions are effective. Okay. So even though it might happen that the energy criteria is fulfilled, on collision they are imparting energy which is greater than equal to threshold energy, but it may happen that the reaction is proceeding at a very slower state. Okay, at a very slow state, indicating that the orientations of the collision were not proper. So orientation is again a very important factor that has to be understood. Okay. So let us take another example. Okay. So basically what I am saying that, okay, so I will say that if we are considering, say, a bimolecular collisions, okay, suppose if we are considering a bimolecular collisions, okay, if suppose we are considering a bimolecular collisions, okay, so we know that suppose the reaction is something like this, A and B are reacting together to form C. Okay, so we know that A and B are colliding together. So I can write the rate of this as K into, if this is elementary step, A into B raised to power 1. Now for knowing the collision theory, we need to understand the concept of collision frequency. How many collisions are happening? So we will talk about collisions per unit volume per unit time. Okay, so we need to understand collision frequency. Okay, so the collision frequency per unit time per unit volume. So basically because this is a bimolecular reaction, so I write this as ZAB. This we have done in gaseous state also. If you don't know the formula, you have to just memorize this, because its derivation comes from statistical thermodynamics that we don't have to study at this level. So basically this is sigma pi sigma square into average speed into n star A into n star B. Okay, so this is the basic collision frequency, where sigma is called as the molecular diameter of AB, or distance of closest approach. Okay, so let me just keep on writing this. So basically, if you look at this, so if this is RA and this is RB, okay, so the distance of closest approach would be when they are just touching each other. So sigma in this case would be RA plus RB. Okay, U average is the average speed. Okay, so this will be 8 RT upon pi mu. Okay, sometimes it is also written 8 KT. Okay, we are writing mu over here because mu represents the reduced mass of a diatomic molecule. If you don't remember the formula, there is no issue. Just so M1 is the molar mass of atom A, M2 is the molar mass of atom B, and just add it. So this is basically the concept of reduced mass. Reduced mass you must have done in your rotation. Okay, so if you don't know the formula, don't worry, you are anyways not going to use this formula anywhere, because we just have to know about the collision theory and not the exact expression. And Na is your number of atoms of A, or number of atoms molecules per unit volume. Okay, so Na star represents number of atoms of A per unit volume, NB represents number of atom of B per unit volume. Okay, I hope this is clear to everyone. So basically, if you look at this, collision theory basically says that more is the number of collision, more is the chances of that the collision produces the product. Okay, so if you increase the temperature, the collision frequency or the number of collision would increase, because it depends upon the molecular speed, as you can clearly see in the expression. So when you increase the temperature, molecular speed increases, number of collision increases, and hence the rate of reaction should also increase. So according to collision theory, the entire reaction is a result of collision. So if we write the rate equation as rate is equals to K, now we have understood that K should be equal to A collision frequency into e raised to minus RT. So this is basically the rate constant. Okay, so that should be the rate constant. K is equals to collision frequency, okay, into the number of or the molecules, fraction of molecules possessing energy greater than activation energy. Okay, so this was basically given by the collision theory. So collision theory basically says that there are two portions in the Arrhenius equation. So it is basically a theoretical explanation of Arrhenius equation. So Arrhenius equation has two terms, A into e raised to minus Ea by RT. E raised to minus Ea by RT represent the fraction of molecules possessing minimum energy, so that reactants are getting converted into product, also known as Boltzmann equation, into the total number of collisions that are happening. Okay, so total number of collisions and fraction of collisions that brings about the fraction of molecules that brings about the change of reactant into product. So the product of this should be the rate constant. Okay, so this was the basic work that was done through collision theory. Okay, I hope you have got this point. If not, just understand that there is a term called collision frequency. You don't have to remember the expressions. This anyways you might have studied in physics as well. If you have forgotten, just don't worry about it. Just remember this, that basically reaction is a result of collisions. So e raised to minus Ea by RT represent the fraction of molecules possessing energy greater than activation energy, and ZAB represents collision frequency per unit time per unit volume. So if you take the product of the two, it should give us the rate constant. Okay, because this will only measure the speed of a reaction. Okay, the number of collisions and number of collisions that are effective in producing the transforming the reactant into product. Okay, so when the value of K was calculated through this, okay, it was found that the experimental value of rate constant was not matching with this K. Okay, that was predicted through collision theory. So there was another factor that was introduced, that is called as orientation factor, which we already said that the orientation is very important for a reaction to happen. So basically collision theory was saying that reactions are the result of collision between the reactant molecule. Only a fraction of molecules that possess energy greater than activation energy would transform into the product. So basically the value of rate constant should be fraction of molecules that can change into product into the collision frequency. But it was seen that even though some of the reactants or some of the molecules had the activation energy, but they didn't transform into the product because their orientation of collision was not proper. So we have to have a orientation factor as well in the expression. So that was taken care by the steric effect. Okay, so basically steric effect is given as, okay, steric effect was given as P. It is represented by P. So is the ratio between the experimental and predicted rate constant. Okay, so basically P tells us the ratio of rate constant that was experimentally determined, that is there in the literature, that we perform in the lab and we get, divided by the predicted or the theoretical rate constant, okay, that we can predict through equations. Okay, So this steric factor take care of the fact that all collisions might not be effective because of orientation factor, because they are not colliding in a framework or in the manner where they can form a product, even though they may be having a very high energy. Okay, so basically that factor is taken care by steric factor, which is also the experimental rate constant divided by predicted rate constant. Okay. So let us look at this example. Now we are saying that suppose NO is reacting with ozone and forming NO2 plus O2. Okay, so what would happen? NO would go and collide with ozone and form NO2 and O2. Now there are many types of collision that are possible. We know that the structure of ozone is bent. Okay, so this is a bent structure. Okay, so this is basically a bent structure. So you can see it is written something like this. So this is a bent ozone structure, bent ozone structure. So NO is going and colliding. Now there are three types of oxygen where it can collide. Okay, it can collide with the center wall oxygen. Okay, so this can go and collide with this oxygen, and it can, if this takes it out, so it will form NO2, and these two oxygen will be liberated out as atomic oxygen. But we know we have to form the product as O2. So basically the NO has to go and attack at this oxygen. Okay, if it attacks at this oxygen, it can, if the collision is effective, this can remove the oxygen from over here. So the two oxygen over here will be released out. Okay, so basically this orientation is not good. Okay, suppose in a case this NO comes and attacks at this oxygen and collides with this oxygen, and it takes out this oxygen along with it. So what will happen? NO2 will be formed and a O2 will be formed. So this orientation is possible. So look at this. So this NO is going and colliding with the oxygen over here. So this collided, okay, but this didn't result in the formation of product. We got back NO and ozone only. Similarly, suppose this was your nitrogen end and this was your oxygen end, and suppose this is your oxygen end and this is your nitrogen end. Okay, so this oxygen went and collided with this oxygen, the oxygen which is at the center of the ozone. Okay, and nothing happened. Suppose something like this happened, that the oxygen approached, okay, the NO molecule, NO can, nitrogen can attack, oxygen can attack. So oxygen attacked at the central oxygen of the ozone, again nothing would happen, okay, and it was ineffective collision. Now suppose the molecule is coming something like this, it is going and colliding with the oxygen. Okay, so it is going and colliding with this oxygen. So this will pick out this oxygen, it will form NO2 and O2. So this is basically a effective collision. So there has to be a particular orientation factor which will take care that the reaction is happening. Okay, so orientation or the steric factor is very important for determining the rate of the reaction. Okay, so without orientation factor, we cannot say that all the collisions are effective, which has the minimum energy criteria. Okay, so only those collisions are effective which fulfills the criteria of minimum energy as well as the steric factor. So steric factor is again a very important factor. Okay, there will be many collisions. Many collisions might have energy greater than equal to activation energy, but still it might not lead to the formation of product because their orientation of molecules during the reaction was not proper. Okay, so this is basically your steric factor. Okay, so if we look at the rate equation now, so we'll say that K is equal to, already I have written this as ZAB, okay, into the steric factor now. Okay, so this is basically the effective, or this is basically the total number of collision per unit volume per unit time. So this is basically collision frequency. Okay, so collision frequency, this includes all the collision, into a steric factor or into orientation factor. Only those, that means these two terms when taken together will tell us the only those collisions which are allowed through orientation, which will result in the product formation, and it has to have a minimum energy that is greater than equal to activation energy. So basically K would be ZAB into steric factor into e raised to minus EA by RT. Okay, I hope you got this now. So basically this is the fraction of molecules possessing energy greater than equal to, okay, the activation energy, and this quantity is basically the number of effective collisions, okay, the number of collisions that are allowed through orientation. So allowed through orientation and allowed through energy. So we are basically taking the product, so that will be the deciding factor for a reaction that will decide the rate constant, okay. So this is basically the energy term, okay, so the energy criteria term. So this is basically the energy criteria term, and this is basically the total number of collisions having proper orientation. So when you multiply this, you get the value of rate constant, okay. So if you remember, we said that through Arrhenius equation, K is equals to A into e raised to minus EA by RT. So you can very clearly see that EA by RT, these terms are common. So basically A, that is the Arrhenius constant, or also called as frequency factor, okay, frequency factor, Arrhenius constant, pre-exponential factor, this is equal to ZAB into P if you just compare the equation, okay. So we can say that the frequency factor or the Arrhenius constant signifies the total number of collisions having a proper orientation, okay. So this is the inference which we can draw from the collision theory. So basically P is known as steric factor, and it is the ratio of the K rate constant experimentally upon K predicted or theoretically, okay. Also we can write P as Arrhenius constant upon frequency factor, or upon collision frequency, okay. So we can basically equate these two, okay. So when you equate these two, we can clearly say that P will be equal to A upon ZAB. So that is Arrhenius constant divided by the frequency factor. So just remember these formula, we will solve some questions on this as well, okay. So this is about the collision theory, okay. So this is again a very important theory that makes us understand a lot of aspect of reactions through its collision property, okay. So basically this is the relationship between the rate of reaction and collision frequency, okay. So we can write the rate constant as K is equals to ZAB into P. P is the orientation or steric factor, ZAB is the collision frequency, e raised to minus EA by RT is your Boltzmann factor, okay. So if we conclude the main points of collision theory, we will say that a chemical reaction to occur, there must be a collision between the reacting species. Only a certain fraction of the total number of collisions are effective in forming the products. Now we have understood that even though collisions might be happening, they might be energetically favorable, but they might not be properly oriented. There has to be certain orientation so that the product are formed. So only few collisions will be effective, and basically we are effective in those effective collisions only. For effective collisions, the molecule should possess sufficient energy as well as orientation, okay. So this is the main point of the collision theory. You can write it down quickly, okay. So I hope these points are clear to you. Now let us understand the effect of catalyst. What does a catalyst do, okay. So basically when we are carrying out a reaction, we say that a catalyst generally increases the rate of reaction, right. Now how does this increases the rate of reaction? Now we know that, let us assume that there is a reaction, hypothetical reaction A plus B is forming a C. This is an elementary reaction, that means it is proceeding in a single step. So basically this is the reactant, this is the product. Now we have understood that every elementary reaction will have a transition state or an activated complex. So basically at some point of time, say this will have a activated complex, okay, which we can write something like this. So it can be anything. So basically it will have a transition state, okay. So depending upon whether the reaction is exothermic or endothermic, we can plot something like this. So this was basically our reactant, this is the product, and this is the transition state TS, okay, or the activated complex, okay. Now basically what does a catalyst do? Now we know that these reactants require this energy to cross the barrier. If this reactant molecules are given activation energy, they will cross the barrier. Okay. So if somehow we decrease the activation energy, if somehow the activation energy decreases, so we know that the barrier is this much. Now if the barrier comes over here, so we know that the value of activation energy has decreased. This means that reaction would become faster. So basically catalyst is doing is, catalyst just goes and stabilize the transition state. So initially the catalyst participates in the reaction, okay, it might get binded to the reactant, and then basically what it does is it stabilizes the transition state through binding, through donating of electrons, through stabilizing the charges. There are many factors. Okay, so the catalyst will stabilize this transition state. So once this transition state is stabilized, its energy will get lowered down. When energy get lowered down, so we know that the activation energy will decrease. So the barrier, reaction barrier would decrease. So the reaction would proceed in the faster manner. Okay, so that is how a catalyst increases the rate of reaction. So very important point that I can say over here is, a catalyst participates in a chemical reaction and is regenerated back. Okay. So we can say that a catalyst participates in the reaction and is regenerated. Okay. So catalyst is basically going and getting just binding to the transition state and stabilizing the transition state. Okay. So catalyst provides an alternate pathway of lesser activation energy. Okay, so that's what we are saying, that when we are not taking the catalyst, the activation energy was high. When we took the catalyst binded with the transition state and stabilized it through some factors which we are going to study when we study the reaction mechanism. So basically it stabilized. So basically the reaction went through a new pathway. So it is providing an alternate pathway of lesser or of minimum energy. Okay, of minimum energy. That's why we are saying that the catalyst increase the rate of reaction. Now, one very important question that comes, does catalyst changes the enthalpy of reaction? Okay, so if you look at the graph, I was saying that the graph would look something like this. So this was the reactant, this was the product, so this was your delta H. Okay, so basically the transition state is stabilizing this transition state. Okay, the catalyst is stabilizing the transition state and not reactant and product, because if it stabilizes the reactant, then the energy of reactant will get lowered. So if the energy of reactant gets lowered, then the activation energy will increase. If the activation energy increases, then the reaction would become slow. So basically we will say that catalyst does not affect thermodynamic quantities. So it does not affect thermodynamic quantities like, we can say, delta H of reaction, okay, equilibrium constant, okay, Kc, Kp, or Gibbs free energy. Okay, so they are not going to be affected by the catalyst. So now what does a catalyst do in an equilibrium reaction? So if you look at an equilibrium reaction, reactant changing into product. Now when we add the catalyst increases both the forward rate of reaction and backward rate of reaction. Okay, so basically it increases the rate of forward reaction and rate of backward reaction, so that equilibrium time is reduced, so that equilibrium is achieved earlier. So catalyst will increase both forward reaction rate and backward reaction rate, so that equilibrium is reached earlier. Okay, but if you look at the equilibrium constant, it is not going to change the equilibrium constant. Okay, so basically catalyst does not affect thermodynamic quantity like Gibbs free energy, equilibrium constant and delta H of the reaction. Okay, so let us look at this graph. So basically we are saying this is the reactant, this is the product, reactant is changing into the product, this is the activated complex or the transition state. So if you look at this, this dark line is the reaction without the catalyst. Now if we took the catalyst, so catalyst we know that is going to stabilize the transition state, so it will bring the transition state from this state to over here. So now the new graph would look something like this, which is shown by a dotted line. Okay, so we can clearly see that the initially the activation energy was this without catalyst. Now the energy of activation would be this, okay, with the help of catalyst. So we can clearly see that when we have taken a catalyst, catalyst has provided an alternate pathway. This was the reaction main pathway, but now it has provided a alternate pathway of lesser activation energy or minimum activation energy. So reaction would proceed through this and it would proceed in a faster manner because activation energy has been reduced. Okay, so just write it down quickly. Similarly, we say that there are two kinds of catalyst. One is a positive catalyst and the other is the negative catalyst. Positive catalyst is the catalyst which increases the rate of reaction. Okay, so such kind of catalyst, when you add in the reaction, it will stabilize the transition state and will increase the rate of reaction. So this is basically example of a positive catalyst. You can see this was the reaction without the catalyst. Now when you added the catalyst, catalyst stabilized the transition state or the activated complex and the activation of the energy of the reaction was lowered. So activation energy was lowered. So this is basically your positive catalyst. Okay, so positive catalyst increases the rate of reaction. So you have to remember positive catalyst will increase, up arrow shows increase. So this increases the rate of reaction. Okay, I hope this is clear to everyone. Now sometimes we also need a negative catalyst. Now why do we need a negative catalyst? Negative catalyst is a catalyst that would decrease the rate of reaction. Okay, so basically this decreases the rate of reaction. Now sometimes we have to study reactions in laboratory which are very fast, which takes place very quickly. So if a reaction is taking place very quickly, we will not be able to study the kinetics parameter or an intermediate or the mechanism pathway of that particular reaction. So basically we need to make that reaction little slow down. So we'll slow down that reaction by adding a negative catalyst. So what does negative catalyst do? Negative catalyst will increase the energy of the transition state. So basically it is going to destabilize the transition state. So initially the transition state was here, so the activation energy was here without catalyst. Okay, now when the catalyst is present, so basically it has destabilized the activated complex, so its energy would increase. Okay, so basically this would increase. Okay, so I will say that this is the activation energy with catalyst. So the activation energy has increased, so the reaction would slow down, and now we can study this reaction. It can either destabilize the transition state and increase its energy so that activation energy is increased, or it can stabilize reactant. If it suppose does not stabilizes transition state but stabilizes the reactant, so reactant will go down, so obviously the energy will also increase. But in general, negative catalyst basically destabilizes the transition state. Okay, so catalyst basically stabilizes the transition state and lowers its energy. Now because it has lowered the energy, the activation energy would decrease. Due to decrease in activation energy, the reaction would become fast. Okay, so now let us do some questions on energy diagram for complex reaction. Suppose we have been given that, suppose we have a reaction something like this, where AB is reacting with say C and forming say AC plus B. Okay, say it is forming AC plus B negative. Okay, suppose this is also C negative. So suppose we have been said that this is a elementary reaction, draw its graph. Okay, so basically when we want to draw the energy diagram profile, so we'll draw the energy versus progress of reaction or the reaction coordinate. Okay, so we know that these are the reactant, so AB plus C is the reactant. So suppose this is the energy level of this, okay, and suppose this is the energy level of product. Suppose this is an exothermic reaction, it could be endothermic as well. So we know that because this reaction has proceeded in an elementary fashion, that it is having only one step. So when it is proceeding, it will have only one activated complex or a transition state. Okay, so this will be the energy diagram. Now suppose we want to consider a two-step reaction. Okay, suppose the reaction is something like this. So AB initially is breaking into say A plus and B negative, and in the second step this A plus is combining with say C and forming AC. Okay, so suppose this is the AC plus. Okay, so suppose this is the reaction, the overall reaction I can write like this, AB plus C changing into AC plus. So this is the basically the main reaction. The question will be like this. This is the reaction and these are its mechanism. So basically this reaction consists of two steps. Okay, 1 and 2. Suppose the rate constant of this is K1 and rate constant of this is K2. We will be asked to draw the energy diagram profile. Okay, so suppose we have been said that the first step is the slow step. Okay, so we know that because the first step is the slow step, that means the reaction is spending more time in the first reaction. Okay, so if it is spending more time in the first reaction, it means that the energy, activation energy of this step would be more. Okay, so suppose this was your reactant AB. Now this is your first step where it is getting transformed into A plus and B negative. So this step will have a transition state. Okay, that is represented by this. Okay, now the second reaction is fast. So it is a fast, so it means that its activation energy would be less. So as soon as this is formed, C would combine and its activation energy would be less, and this would be the final formation of product. Okay, so this would be the transition state of second reaction. So this is how we are going to predict. Suppose graph was given to you, we can easily understand that the activation energy of this step was higher. Okay, this is higher activation energy, that means this is the slowest step, that it will take more time in crossing the barrier. So this is the slowest step and this is the fast step. Okay, so every elementary reaction, one reaction, a single elementary reaction will always have a transition state, one transition state. So the first step will have one transition state, second step will have one transition state. Okay, so this is how the energy diagram will look. If suppose in the question it says that second step is the slowest step. So when second step is the slowest step, we can say that the first step would be fast. Okay, so the activation energy suppose is this. Okay, so this is A, B, okay, and this is A plus and B negative. Now second step is a slow step. Suppose if it is given to us that second step is the slow step, it means that the activation energy of the second step would be more. So the graph would look something like this. Okay, whether a reaction will be exothermic or endothermic, it depends upon the energy criteria that has been given to you. We cannot say that this is endothermic or exothermic. The quantity will be given to you. Okay, so we should know the energy of reactant and product to predict whether the reaction is endothermic or exothermic. So this is how you go on to make the energy diagram profile. So for one elementary step, we'll have one transition state. So basically, if there are four, say elementary reaction in a complex reaction, so we'll have 4 peaks, and that peak will be the highest, which is slower, so that it has higher activation energy and it proceeds slowly. Okay, so just draw it quickly. I hope this is clear to everyone. So in case you are having any doubt, please write to me immediately in the chat box so that I can understand whether you are able to understand the concept that has been demonstrated till now or not. If you are liking the lecture or if you are having no issue, if you are understanding everything, you can also write yes sir, so that I can understand that everything is going fine. Okay, so just Just type it out. If you are understanding everything, please write yes sir. If you are facing any problem, just write having a conceptual issue or having any problem, so that I will be able to rectify it. Keep on interacting. That is the beauty of Yup Master. Okay, my purpose of leaving a offline system and coming to online system is I want to reach to everyone. The students whom I was not able to cater till these year in my 12 years of experience. So I want to cater to all the needs of the student present out there. But you have to be interactive to make me understand what kind of content basically I need to give to you. So you can write, I am liking the lecture, I am not liking, I am disliking. So if you interact, we'll build a very good relationship, and then we'll be able to work in a much better manner, and we'll be able to get better results. Okay, so interaction is very important. You need to interact. That's how we are going to change the results that we are sitting at right now. Okay, so I hope this is clear to everyone. Similarly, we can draw for a 3-step also. Okay, so let me just quickly show you for a 3-step. Suppose a reaction has been given to you, A changing into B, this is K1, this is changing into C, K2, this is changing into D, K3. So suppose this is given as slow step, this is a fast step, this is a fast step. Okay. Now suppose it has been given that K3 is much greater than K1 and K1 is greater than K2. Okay, so we know that K3 is very fast, K1 is again fast, but K2 is very small and it is very slow. So if you draw the energy diagram profile, so we know that there are 3 reactions going on. Okay, so 3 transition state would be there. Now first reaction was, suppose this is the A and this is B. Okay, so this is transforming into A into B. This is the transition state related to it. Now when B is transforming into C, okay, this is a slow step. So this activation energy would be more than this activation energy. So make sure that you are drawing something like this. Okay, so that you can clearly understand that this activation energy is more than this. Okay, now the last step where C is getting converted into D, just quickly drop this now. Okay, because we know that this is the fast step, K3 value is the highest, so this reaction would be very fast, so the activation energy would be low. So this is the graph. Similarly, you can plot any of the graph by just changing, this becomes slow, these two become fast, or that becomes slow and these become fast. Okay. So let us just look at one question before we end the session. Okay. So basically this says that in chemical kinetics, only a small fraction of collisions lead to reactions. We know that this is a completely true statement now, because the colliding molecules may not be properly oriented to one another and the collisions are not energetic. Okay, so this looks a perfectly placed answer for this question. Okay, we know that only small fraction of collisions lead to the reactions because all collisions are not energetic enough and they might not have the proper orientation. Okay, so this appears to be a very correct question. The colliding molecules are properly oriented to one another and the collisions are highly energetic. Okay, so this is completely wrong. Okay, if this is the criteria, then obviously the collisions are effective. Effective collisions are those which are energetically allowed, which have the proper energy to bring about the transformation of reactant into the products and are properly oriented. The colliding molecules are properly oriented to one another and the collisions are not energetic. Okay, so this can be the answer as well. The collision molecules are oriented but they are not having the proper energy. So again, it will not lead to a reaction. So if it is a multiple choice, this could be a correct answer. The colliding molecules may not be appropriately oriented to one another and the collisions are very energetic. Okay, so this is again the right option. Okay, so if it is multiple choice, then ACD would be the answer. If it is a single choice, then we have to look for the best answer, and the best answer over here would be A. Okay, only small fraction of collisions are allowed. Okay, because all collision molecules may not be properly oriented and the collisions might not be energetic. But C and D options are partially correct, because if orientation is not there and energy factor is realized, then also it is not called as a effective collision. If energy is very high than required, but collisions are not good, or the collisions are not properly oriented, then also we can say that it is an ineffective collision. Okay, so this was the question. So this would be the question for your day. You can take it as a homework. You can have a quick snapshot of this. Okay, this was basically asked in JEE Advanced 2017, a multiple choice question. Okay, so just once you are done with the lecture, once you go through this lecture which was taught today and you solve the daily practice problem sheet, then after doing that, just look at this question. Okay, we'll discuss this question in the next class, so that this will also give you the idea what kind of questions are asked in JEE Advanced. Okay, so this is basically a purely theoretical question. This 2017 topper Sarvesh Mehtani. Okay, I think everyone might be knowing Sarvesh Mehtani was basically, again I had this opportunity to mentor Sarvesh Mehtani in Chandigarh. So 17 and 18, 2 years back to back, like my student got the rank 1. It was not because of me, obviously. Those students were talented. They just got the right direction and right kind of training with all the people that were involved. So I cannot be basically called as the creator of that rank. That knowledge, that amount of passion was there in the student. It was just that he needed a proper orientation, like the orientation which we are discussing over here. Okay, so a right concept building, a right approach to the problem solving, creating a very important theoretical aspects is very important in chemistry, because you don't know what kind of question will be there. So theory is equally important as compared to the numerical solving. Okay, so I hope you are liking these lectures, you are able to understand this chapter. We are about to end this chapter now. Like, if you see the JEE requirements, we have completed the chapter according to the JEE requirement. In the next class, we are going to talk about parallel and sequential reaction that are not there in the syllabus, but is often you study that in nuclear chemistry or in the atomic physics. Okay, but we are going to cover this because it is there in the Olympiad syllabus as well. Okay, so I hope everyone out there is liking the lectures. If you are having any issue, not able to solve any DBB, you have to write to us so that we can understand. And if you are liking these lectures, we would like to have some comments from you. You can just type it out, type your reviews on the app itself right now, so that we can have a look. And if any problem, if any issue you are facing, you can also write it, so that we will be able to cater you in a much better manner and come with more better solutions for your preparation. Okay, so this is Animesh signing off for now. We'll catch in the next session.